From the time of Aristotle, several hundred years BC, to about the year 1500, when Galileo came along, not a lot of progress was made in physics. Our foundation was wrong, and when you try to build on a weak foundation, you don't get very far before everything crumbles down. Galileo came along roughly in the year 1500, and he got this idea about inertia. And that helped transform the way we thought about motion, and all kinds of progress took place after that. It's said he got the idea using inclined planes. So he would set up an incline like this, and he'd release a marble on the ramp at some height. The marble would roll down the ramp and back up the other side. And where did the marble stop approximately? Approximately at the same height it was released from. So if you release the marble at a certain height, it gets almost to the exact same height on the other side. Then Galileo said, well, wait a minute, what would happen if I took my ramp and I pulled on it and bent it so it was a little bit longer on this side? I'm going to release my marble over here from this height, and it's going to start to roll down the ramp and up the other side. And when's it going to momentarily come to rest? When it gets to roughly the same height it was released from. When it gets to about the same height it was released from, it momentarily comes to rest and then goes back down the incline. And then he said, wait a minute, what happens if I bend that ramp down? So it's perfectly horizontal. I'm going to let go of my marble over here. It's going to roll down the ramp and along this side. And what's it going to do? It's going to keep going forever. And that is correct. Galileo discovered this, and when he realized this, an object in motion will just keep moving in a straight line at a constant speed, keep moving with that exact same motion until a force acts on it and changes its motion. Or another way of thinking of it is an object at rest will continue at rest. It doesn't just get up and start moving on its own. It stays at rest until a force acts on it and causes it to move. This is the idea of inertia. An object at rest remains at rest until a force acts on it and causes it to move. And an object in motion stays in motion until a force acts on it and changes that motion. I just told you that this was Galileo's observation. We're discussing Newton's laws here. Well, in the same year that Galileo died, Newton was born. And a few years later, maybe more than a few years, he came up with his laws of motion. And he said the idea of inertia is so important, so fundamental to understanding motion, he restated Galileo's idea as his first law of motion. So inertia is known as Newton's first law. It was Galileo's discovery, and Newton said, it's so important, it has to be the first law because everything else builds on that. Until you understand that, you can't figure out motion. The next thing he said was his law, Newton's second law. The net force is equal to the mass times the acceleration. Maybe a more intuitive way of thinking about that is to move some things around there and say the acceleration is equal to the net force over the mass. What does that mean? Acceleration is change in motion. What does it take to change something's motion? It takes a force. There has to be a net force acting on our object to change its motion. What prevents the object from changing? What makes the object resist changes in motion? Inertia. And that's what m is. That's how we measure inertia. That's the quantitative measurement for inertia. The acceleration of the object is proportional to the net force acting on the object. And it's inversely proportional to the inertia, the mass of the object. We can write that as sum of the forces equals ma, or if you prefer, the net force is equal to the mass times the acceleration. Those say the same thing. But don't forget, this is a vector equation. The direction of the force is the same as the direction of the acceleration. Those are the only two vectors here. Mass is just a scalar. It's a proportionality constant. And Newton's third law says that when two objects interact, remember, forces are interactions between objects. When two objects interact, the force that object A exerts on object B is equal and opposite to the force that object B exerts on object A. They have to have the same magnitude force, and it has to be in opposite directions. If I draw two objects crashing into each other, at the instant they collide, there are forces. A and B are interacting, and they exert forces on one another. So if we draw a free body diagram for A, we would see there's a normal force. There's a force of gravity. I'll put normal force on A. And there's a force from B pushing on it. Force B on A. If we draw a free body diagram for block B, we would see a normal force and the weight. And we would see a force from A pushing on it. So you can see that these forces have to be in opposite directions. If A bumps into B pushing it in this direction, B is, in essence, bumping into A pushing it the other way. The forces are in opposite directions. And if you carefully look at momentum conservation, you'll see that the forces have to be equal in magnitude. They have to be equal in magnitude and opposite in direction, because when A and B are colliding and pushing on each other, they interact for the same amount of time, right? A cannot push on B for a longer period of time that B pushes on A. The time has to be the same. And impulse is force times time, which is change in momentum. And if this is an isolated system right here, and there are no net forces acting on them, A and B are on frictionless wheels when they collide, then we know momentum is conserved, so there's no change in momentum. So that logic brings us to the fact that the impulses have to be equal and opposite, so the forces have to be equal and opposite because the time is the same. Maybe Newton's third law comes from momentum conservation may be momentum conservation comes from Newton's third law, but they're kind of two ways of saying the same thing.